Okay, in this lecture we're going to finish the section 1.6 material on applications of linear systems. And in this last part of the lecture, we're going to be looking at a network flow problem, one nice application of linear systems. So let's start by introducing a little bit of terminology. So here, when we're talking about a network, what is a network? Well, it consists of a set of points, which are called nodes, with lines or arcs called branches, which are connecting either some or all of my nodes. Now the direction of flow in each branch is indicated by an arrow. So the direction of flow is given by some directed arrow or arc. And the flow amount or the rate of flow is either shown or is denoted by some variable if the rate of flow is unknown in a given direction. So our basic assumption in these network flow models is that the total flow into the network has to equal the total flow out of our network. And additionally, the total flow into any node has to equal the total flow out of that node. So our problem of interest in analyzing a given network is to determine what is the flow in or the flow out along each branch or into or out of each node. So a classic example for a network flow problem is traffic flow. So let's consider the network which is illustrated below. Here we're describing the traffic flow measured in vehicles per hour over several streets. Here we've got 4 streets, and we're considering the flow among traffic through the intersections of these streets. So in this problem, let me start by labeling each of my intersections as a node. Here I'm going to label these as A, B, C, and D. My 4 nodes indicating these 4 intersections. And from our diagram, we're given information about the traffic flow into and out of each of these intersections or nodes. So we know the basic assumption for these network flow problems is that the rate of flow in has to match the rate of flow out. So let's look at the rate of traffic flow into and out of each intersection or node. So starting with intersection A, well, the rate of flow into intersection A must match the rate of flow out. So let's start with the rate of flow into intersection A. So looking at the arrows moving into node A, we have a X4 and a 610. These would be vehicles per hour coming into node A. So that flow in, X4 plus 610, has to equal the flow out. So looking at the flow out from node A, well, we have X1 plus 450 vehicles per hour moving outward from node A. So here we have X10 plus 450 as our flow out. It must equal the flow in. Now for node B or intersection B, let's look at our flow in. So we just saw from node A to node B, we have a rate of flow of X1. Now also coming into node B, we have a 400. So this rate of flow in to intersection B is X1 plus 400 vehicles per hour. That has to equal the rate of flow out, which looking at our outward arrows from intersection B is X2 plus 640. So let's move through our other 2 intersections. For intersection C, the rate of flow in is going to be given by X2 plus 600, 600 coming in from out of our system. And the rate of flow out from node C or intersection C is X3. So this X2 plus 600 must equal X3. And for intersection D, we have the rate of flow in is x3, which has to equal the rate of flow out, which we can see is given by this x4 plus 520. So we have here a system of linear equations representing this traffic flow or network flow. We might want to simplify each equation so that it's a little bit easier to work with. So starting with my first equation for node A, well, let's just move all of our variables to one side of the equation. So throughout these, let me maybe move everything to the left-hand side of each equation. So moving everything to the left-hand side in equation A, I have minus x1 plus x4. So I'll move my variables to one side, a negative x1 plus x4, and that's equal to, I'll leave all of my constants on the right-hand side, so I would have 450 minus 610, which is negative 160. Now in my second equation, equation B, moving all of our variables to the left-hand side, we have a positive x1 minus x2 is equal to, our constant would be 640 minus 400, so 240. For equation C, we would have x2 minus x3 is equal to negative 600. And for equation D, we have x3 minus x4 is equal to 520. All right. So we have the following system of four linear equations in four variables, x1 through x4, which is what we were asked to find in part A. So then, of course, in part B, we are asked to solve this linear system in order to determine the general flow pattern for this network. All right. So here, we want to express our system of equations as an augmented matrix. So as an augmented matrix, let's write out our system. Four equations and four variables. Our first equation was negative x1 plus x4, so we had 0, x2, and x3, plus 1, x4, was equal to negative 160. Our second row would be 1 minus 1, 0, 0, 240. Our third row is 0, 1, negative 1, 0, negative 600. And our fourth row is 0, 0, 1, negative 1, 520. All right. So we want to row reduce this in order to solve. So a few ways we could proceed here. So my leading entry in my first row is a negative 1. I know that I want that to be a positive 1. So an easy way to get that would be to take the negative of my first row. So one operation which I will perform in this first step is to take the negative of row 1, which would give me positive 1, 0, 0, negative 1, positive 160. And in this same step, I know that for this first column, everything below that leading entry I want to have as a 0. So I need to kill off the leading 1 in my second row. And an easy way to do that is using the negative 1 that we had for the lead entry of our first row. So here I could take row 2 and add row 1 to it, which would give me 0, negative 1, 0, 1. And then my 240 minus 160 leaves me with 80. All right. And for now, my last two rows I'm going to leave alone. All right, so I now have a 1 for the leading entry of my first row. The leading entry of my second row is a -1, and below that we have a +1. So in a similar fashion to what I did in the first step of my row reduction, I'm going to take the negative of my second row to get a +1 term there. And to eliminate the leading 1 in the third row, I'm going to add the second row to the third. So one operation which I will perform is to take the negative of row 2. So my first row will remain 1, 0, 0, -1, 160. My second row becomes 0, 1, 0, -1, -80. And in this same step, I'm going to take row 3 and add row 2 to it, which will give me 0, 0, -1, +1, and then my -600 plus 80 will leave me a -520. And my last row I will leave as 0, 0, 1, -1, 520. So at this stage, you might notice your last two rows are identical, just negatives of each other. So they will cancel, or they represent the same linear equation. So we're going to end up having a free variable. But let's simplify a little further to proceed and see how this works out. So our first two rows have a lead entry of 1 with zeros above and below. Our third row has a leading entry of -1, which I want to be a +1. And then I want to eliminate the factor of 1 that appears in the fourth row below that. So as we did with our first two row operations, let's get rid of the negative in that third row by taking the negative of my third row. So here we have 1, 0, 0, -1, 160, 0, 1, 0, -1, -80, 0, 0, 1, -1, 520, and in the same step I'm going to take row 4 plus row 3, which leaves me 0, 0, 0, 0, 0, since our third and fourth rows we said were identical. So now we have 1s for the lead entries in our first three rows with zeros above and below each of those leading entries. So this matrix is in reduced row echelon form, and we see that our fourth column corresponding to x4 does not have a pivot. Therefore, we could let x4 be a free variable. So here we will let x4 be a free variable. Now to solve for our other variables in terms of this free variable, we can look back at our previous rows. So using the first row, we find that x1 minus x4 has to be 160. Using the second row, we have x2 minus x4 is -80. And for our third row, we have x3 minus x4 is 520. So solving for x1, we have x4 plus 160. X2 is equal to x4 minus 80. And x3 is equal to x4 plus 520. So here we have a solution set where our solution set would be of the form x1 is equal to x4 plus 160, x2 is x4 minus 80, x3 is x4 plus 520, and x4 was some free variable. Now, one thing that we need to be a little bit careful of is the sign for each of these x values. So if, for instance, let's look back at our traffic diagram, it looks like these streets are each one-way streets. That is, the flow of traffic is in any one direction along any of these streets. So in order to maintain the flow of traffic in those directions, we need each of these variable values, x1, x2, x3, and x4, to be positive. If we had a negative value for any of those variables, that would be reversing the direction of traffic flow. So we might have traffic that's driving in the wrong direction, for instance, which wouldn't be possible for our analysis of this system. So if we need all of x1 through x4 to be positive, well, let's be a little bit careful about how these values are defined. So x1 here was x4 plus 160. So as long as x4 is positive, we're good. But x2 was defined as x4 minus 80. So in order to ensure that we do not have a negative value for x2, we need x4 to be at least 80. And for x3, we had x4 plus 520, so as long as x4 is positive, x3 will remain positive. So when we write out our solution set here, we might make the restriction, instead of allowing x4 to be any real number, we would specify that x4 needs to be greater than or equal to 80 in order to ensure that we don't have traffic moving in the wrong direction. And that is to ensure that x2 remains